Hello dear student, welcome back. So today we are going to learn application of electromotive force series. So let's start with the first one, that is called as the application of EMF series in terms of reactivity of metals. Reactivity of metals. Okay. So the activity of the metal depends on its tendency to lose electron. Okay, for example, metal loss electron converted to m plus n electron. Okay, this tendency depends on its value of SRP, that is called as standard reduction potential. Okay, now as we know, the metal with very low SRP value, okay, or highly negative SRP value are most reactive and quickly lose electron to form cation. Okay, to form cation. Clear? Now the chemical reactivity of various metal increases down the EMF series as negative value of SRP increases. Clear? So जितना ज़्यादा नेगेटिव स्टैंडर्ड रिडक्शन पोटेंशियल होगा उतनी ही मेटल ज़्यादा रिएक्टिव होगी. ठीक है. नाउ लेट्स से फॉर एग्जांपल alkali metals and alkaline earth metal. Okay, alkali metals and alkaline earth metals, okay, having highly negative standard reduction potential value. Okay, hence they are more reactive. Okay, how do we identify their reactivity? They even react with cold water, okay, and evolve hydrogen gas. Okay, just for example, sodium when reacts with water, it will form sodium hydroxide. Okay, and dihydrogen gas is reduce, highly exothermic reaction. But sodium can react with water, okay, even in cold conditions. Similarly, calcium when reacts with water, okay, it will form calcium hydroxide and dihydrogen gas is evolved, okay. So the reaction with cold water, this indicates their highly reactive nature. Now if we talk about the second type of metal, okay, so metals like iron, lead, okay, tin, nickel, cobalt, etc., okay, with which lie little down the hydrogen, okay, down the hydrogen in EMF series, okay. Do not react with cold water, but react with steam to evolve hydrogen, क्लियर. सो यहाँ पे टेम्परेचर थोड़ा ज़्यादा चाहिए फॉर रिएक्टिविटी विथ वाटर. नाउ द नेक्स्ट वन, metals like copper, silver, mercury, okay, gold, etc., which lie above hydrogen in EMF series, okay, do not react with cold water or steam to evolve hydrogen gas, okay. Hence they are least reactive metal, okay. What we can write, hence they are least reactive metal, okay. So this is the application with respect to the activity of the metal. Now second, we will discuss about the electropositive character of metals. This is also related to the tendency to lose electron, okay. So the electropositive nature of any metal is related to tendency to lose electron, which depends on its SRP value. Clear? Now if we make a list, then which are strongly electropositive metal, okay. So metals having standard reduction potential reduction potential near about minus 2.0 volt, okay, or more negative than that, okay, like alkali metal and alkaline earth metal, okay, are strongly electropositive. Clear? Now let's talk about the moderately electropositive metal, okay. So if we think about the moderately electropositive metal, then we can write metals with reduction potential value lie between 0.0 and minus 2.0 are moderately electropositive. Clear? What are the examples of moderately electropositive metal? Aluminium, zinc, okay, Fe, cobalt, nickel, etc. are moderately electropositive. Clear? Now let's talk about the third type. They are called as weakly electropositive metal. So what you can write, the metals which are placed above hydrogen in EMF series and having positive SRP value are weakly electropositive metals, okay. Now examples of weakly electropositive metals, as we had discussed earlier, copper, mercury, silver, aurum, okay, etc. belongs to this group. Clear? Now the next application of EMF series is about displacement chemical reaction. Okay. Now if we want to predict whether a given metal displaces another from its salt solution, then as per the law, a metal present at lower position in EMF series, okay, will displace the other metal from its salt solution. Clear? The other metal should be placed at higher position in EMF series compared to first metal. Okay. In short, more reactive metal displace less reactive metal from its salt solution. Clear? Now, with respect to standard reduction potential value, what we can say about the identification of displacement reaction? So, what you can write, the metal with low SRP value can displace the metal with high SRP value from its salt solution. Okay. Now let me give you one example. So suppose standard reduction potential of zinc, okay, E naught zinc plus 2 zinc has value minus 0.76 volt, and standard reduction potential of copper in terms of copper plus 2 copper, that is plus 0.34 volt. Okay, so you can write it has low SRP, hence it is more reactive. Okay, and this one has high SRP value compared to zinc, and hence it is less reactive. Okay, so as per the value we can say that zinc displaces copper from its salt solution. Okay, so the displacement reaction is zinc plus aqueous solution of copper sulfate. Zinc displaces copper from its salt solution, it itself get oxidized to zinc sulfate, and copper plus 2 ion reduced to copper. Okay, this reaction we had learned in galvanic cell. Now let's talk about the displacement reaction of non-metal. Displacement reaction of non-metal. Okay, so if we think about the displacement reaction of non-metal, okay, then a non-metal with high SRP value and lies at higher position in EMF series compared to other non-metal with less SRP value, okay, and lie at lower position, okay, will displace displace it from its salt solution. Okay, or you can say more reactive non-metal will displace less reactive non-metal from its salt solution. Okay, now the example what we can write over here is chlorine is one non-metal when it reacts with potassium iodide solution. Then chlorine displaces iodine, okay, and it converted to potassium chloride, and iodine is going to be liberated. So what is the oxidation number of chlorine? Oxidation number, element 0, iodine -1, chlorine -1, iodine 0. So 0, 2 minus 1 chlorine itself get reduced, okay, and iodine, okay, itself get oxidized. So here it is going to be proved that the non-metal with high SRP value like chlorine get reduced, and other like iodine, okay, get oxidized, okay. So this way you can understand the displacement reaction in non-metal. Second example, again chlorine when reacts with potassium bromide, chlorine displaces bromine, okay, as in form of Br2. Okay, now let's discuss the displacement of hydrogen from dilute acid by metal. Okay, so displacement of hydrogen from dilute acid by metals. So what we can write? So the metal which can provide electrons to proton H plus ions present in dilute acid for reduction evolve hydrogen gas from dilute acids. Clear? The general reaction we can write any metal M when oxidized to M plus N electron, that electron will be received by proton and it converted into H2. Clear? Now who can do this? The metal with very less or more negative SRP value and lies below the hydrogen in EMF series can displace hydrogen, okay, from solution of dilute acid, okay, like zinc metal dilute HCl solution give zinc chloride plus H2 gas is liberated, okay. So position of zinc is below the hydrogen in EMF series. Now the metal which are placed above the hydrogen in EMF series like copper, mercury, silver, aurum, platinum, okay, do not evolve hydrogen from acid solution, okay. So this is also based on the reactivity point of view. Now if we think about the reducing power of the metal, okay, reducing power of metal present in the reactivity series, then what you can write, reducing nature depends on reducing nature of metal depends on its tendency to lose electron, clear. Now more negative SRP value of any metal, it has more tendency to lose electron. More negative SRP value, okay, more the tendency to lose electron, and more stronger reducing nature, more stronger the reducing agent, okay. So what we can say, a power as reducing agent increases as the SRP value of metal become more and more negative, okay, more and more negative, clear. For example, if we take some of the metal from reactivity series, sodium, zinc, Fe, okay, and if we compare their standard reduction potential value, then this is 2.7, okay, this is minus 0.76, this is minus 0.44. So the one which has a more negative SRP value has a stronger reduction potential, okay, or reducing nature. Similarly, if we can write about the oxidizing nature of non-metal, okay, so oxidizing nature of non-metal. So what we can write about it? Oxidizing nature of any non-metal depends on its tendency to accept electron. Okay, so more the value of standard reduction potential, more the value of standard reduction potential, more will be tendency to gain or accept electron. Okay, and stronger oxidizing power. Clear? So we can write that the strength of an oxidizing agent increases as the value of standard reduction potential become more and more positive. Clear? So if we think about the element and their standard reduction potential value, iodine, bromine, chlorine, fluorine, okay, then the value are 0.53, 1.06, 1.36, 2.85. now as you can see, value of SRP become more positive, strength as oxidizing agent increases. Okay, so you can write the order like this. Okay, now the value of SRP is also related to stability of oxides. Okay, so what we can write about the stability? The thermal stability of metal oxide, depends on its electropositive nature. Okay, as the electropositivity of metal increases down the EMF series, okay, the thermal stability of metal oxide increases. Okay, thermal stability of metal oxide increases. The oxide of metal, the oxides of metal, okay, having high positive SRP, okay, are not stable towards heat. अब हमें पता है कि कौन से ऐसे मेटल है जिसकी SRP वैल्यू पॉजिटिव है, ओके। द मेटल विच प्रेजेंट above copper in EMF series, okay, form unstable oxides, okay. So what we can write as an example, silver present above the copper in EMF series. So silver oxide, when we heat it will easily decompose to silver and oxygen gas is released, okay. Mercury oxide, okay, also heat unstable, okay, and it will get decomposed to mercury and oxygen gas is liberated. So in both case you can write that they are thermally unstable, clear. Now which oxides are thermally more stable? So sodium oxide, calcium oxide, okay, barium oxide, all of these, aluminum oxide, all oxides are heat stable oxides. So thermal stability also we can predict from the SRP value. Next application of EMF series is that prediction of anode and cathode of electrochemical cell, okay, and calculation of cell potential. So EMF series provide the value of standard reduction potential of given electrode present in electrochemical cell. So if we know the standard reduction potential value of electrodes, okay, present as redox couple in any electrochemical cell, okay, then generally the electrodes with high SRP value can act as cathode, and the electrodes with low SRP value can act as anode, okay. Now what is cell potential? Cell potential, or you can say standard cell potential, it is the difference in the value of standard reduction potential of cathode and anode. So if you are knowing the SRP value of cathode and anode, you can calculate the standard reduction potential also. Okay, so the equation is standard cell potential is equal to E naught cathode minus E naught anode. Okay, so that is E reduction cathode minus E reduction anode. Clear? You can calculate the cell potential by this equation also. E naught cell, that is E oxidation potential of anode plus standard reduction potential of cathode. Clear? Or E naught cell is equal to E naught oxidation anode minus E naught oxidation potential of cathode. But generally the first equation is used repeatedly to calculate the standard cell potential of the given electrochemical cell. Okay. Next application is nature of cell. Okay, next application is identifying the nature of the cell. What do you mean by nature of the cell? Means reversible or irreversible. Okay, if we want to identify the reversible or irreversible nature of the cell, then you can write a cell is said to be reversible if following conditions are fulfilled. Okay, what are these conditions? So the first condition is the chemical reaction of cell stops, okay, when exactly equal external EMF is applied. Okay, अगर इक्वल एक्सटर्नल EMF अप्लाई करते हैं और केमिकल रिएक्शन ऑफ द सेल स्टॉप हो जाती है, ठीक है, सो इट मीन्स दैट the cell nature must be reversible. Okay, now let's write the second one. The chemical reaction of cell is reversed and the current flow in opposite direction when external EMF is slightly higher than actual EMF of cell. Clear? So if you provide the external slightly higher than EMF, cell is reversible. Cell is reversible. Clear? If any cell, if so in short we can write that if E external is greater than EMF, cell reaction will be reversed. Okay. Now, if any electrochemical cell, okay, do not obey the above conditions, then it is called as irreversible cell. Clear? Daniell cell is an example of reversible cell. Okay, Daniell cell is an example of reversible cell. Now, the next important